Hello all. In this lecture, we will discuss full order state observer. Um, in the full placement approach, the design of control systems, we shall have all the system states, all the X's are available for feedback to be fed back in the system and used for state observation or for state feedback and control, controlling the poles to be placed at the desired locations. In practice, not all the system states or state variables are available for feedback. Some of these states cannot be uh, measured, maybe in inaccessible location, or sensors are expensive to um, measure these states. Then we need to estimate the unavailable state variables. Estimation of unmeasured state variables is commonly called observation. A device or a computer program that estimates or observes the state variables is called state estimator or state observer, or simplified as observer. We have two types of state observers. The first one is the first of full order state observer. If the state observer can observe all the state variables of the system, regardless of whether some state variables are available for direct measurement, this is called the full order state observer. For the reduced order, if the state observer observes only those state variables which are not available for direct measurement, only the states that are not available for direct measurement, this is called the reduced order state observer. Topology of state feedback control with observer-based approach. State feedback with a state observer, we have the plant, the observer which observes the output of the system and use it to control, to estimate the states of the system, then input these states, estimated states to the controller for feeding back to the system. This is the shape or the block diagram of the state observer. We take the output Y and compare it to the estimated Y, the estimated output. Then we get the error multiplied by a constant K, then is used for input. The input is used to get the estimated states, and these estimated states are fed back to the original system for use to obtain the output. This is the same as the previous slide. Now state observer estimates the state variables based on the measurements of the output and control variables. Therefore, the system must be observable. The concept of observability plays an important role in this state observer design. State observer can be designed if and only if all the observability conditions are satisfied, if the system is completely state observable. We have the system of state variables, x dot equals ax plus bu and y equals cx. The mathematical model of the observer is the same as that of the plant. It has the same model of the plant, except we include an additional term, and this term that includes the estimation error to compensate for the inaccuracies in the matrices A and B and lack of initial conditions if we don't have initial conditions. The state error or observation error is the difference between the measured output and the estimated output. We have seen in the figure in the previous slides. The initial error is the difference between the initial state and the initial estimated state. It's a difference between this difference between initial state and the initial observed state or estimated state using the state observed. We have x hat dot equals a x hat plus bu plus k y minus cx hat, or cx hat is the estimated out. X hat is the estimated state vector, Cx hat is the estimated output, and Ke is the observer gain matrix, the gain matrix for the state observer. The order of a state observer will be the same as the order of the plant, as it is a full order state observer. We will now consider the plant defined by the equation a x dot equal ax plus bu and y equal tx. For the state observer equation, we have x hat dot equals ax hat plus bu plus ke times y minus c x hat, which is estimated out. To obtain the observer error equation, we subtract equation 2 from equation 1. We get x dot minus x hat dot equals ax plus bu minus ax hat plus bu plus ke times y minus c x hat. Then we will enter the sign or multiply the sign by the bracket. We get negative ax hat minus bu minus ke times y. We substitute y by cx minus cx hat. Then we have x minus x hat dot equals ax plus bu minus ax hat minus bu minus ke times cx minus cx hat. We merge these two terms and take a as a common factor. A times x minus x hat, b minus bu cancel those plus bu minus ke times c. We get c as a common factor, x minus x hat. The difference between x and x hat is the error vector, where the error vector is x minus x hat. Then we substitute e equals x minus x hat. We get e dot equals ae minus ke times ce. We can take e as a common factor. Then we have e dot equals a minus ke times c. From this equation, we see that the dynamic behavior, all the dynamics of the error vector is determined by the eigenvalues of the matrix A minus KEC. If matrix A minus KEC is a stable matrix, the error vector will converge to 0 for any initial condition of E of 0. X hat of t will converge to x regardless of the values of x naught if the system matrix or the matrix A minus KEC is a stable matrix. If the eigenvalues of matrix A minus KEC are chosen in such a way that the dynamic behavior of the error vector is asymptotically stable or critically stable and is adequately fast in the response, then any error vector will tend to 0, can reach to 0, the origin, with an adequate speed, with a speed which is acceptable. If the plant is completely observable, if we check observability and get that the system is completely state observable, then it can be proved that it is possible to choose KE such that A minus KEC have the arbitrarily designed eigenvalues. We can choose matrix KE to get the eigenvalues required for the A minus KEC matrix. The observer gain matrix KE can be determined to yield the desired matrix A minus KEC. And the design is about getting KE. Duality property. The design of a full order observer becomes determining the appropriate KE such that A minus KEC has the desired eigenvalues or the designed poles for the system. The problem here becomes the same as the pole placement problem. This is like the pole placement problem. In fact, the two problems are mathematically the same, mathematically as steps. This property is called the duality between the design of a state observer and the pole placement. X dot equals ax plus bu and y equals tx system equations. In designing the full order state observer, we may solve the dual problem. What is the dual problem? We have the pole placement problem for the dual system. Z dot equals A star Z plus C star V and N equals B star Z. Assume that the control signal V equals negative K Z. The dual system is completely state controllable. Then the system feedback gain matrix K can be determined such that A hat minus C hat K will yield the set of desired eigenvalues by the system. We have the eigenvalues mu1 to mu(n). These are the desired eigenvalues of the state observer matrix. Then by taking omega i's as the desired eigenvalues of the state feedback gain matrix, the dual system we obtain Si minus A star minus C star K equals the S minus mu1 times S minus mu2 until S minus mu(n). Noting that the eigenvalues of A star minus C star K and those of A minus K star C are the same. We have Si minus A star minus C star K equals Si minus A minus K star C. Then comparing the characteristic equations Si minus A minus K star C and the characteristic polynomial for the observer, which is Si minus A minus KEC, we have Ke equals K star, are related by Ke equals K star. By using the K matrix determined by the pole placement approach in the dual system, the observer gain matrix Ke for the original system can be determined by Ke equals K star. We can design the observer gain matrix using direct substitution method, Ackermann's method, or using the transformation matrix Q. The direct substitution method, we assume that Ke equals K1, K2 until Kn, the order of the system. The feedback signal through the observer gain Ke serves as a correction signal, that corrects the plant model to account for unknowns in the plant. We have some unknowns in the plant, and Ke will account for the unknowns in the plant. If significant unknowns are involved, the feedback signal through Ke should be relatively high. If we have a significant amount of significant unknowns that are not known in the system, then we will have large Ke. However, if the output signal is contaminated significantly by disturbance, if the output is having a great disturbance and measurement noise in the measurements we have, then the output Y is not reliable, and the feedback signal should through the matrix Ke should be relatively small. It is adjusted to be relatively small in this case. The observer gain matrix Ke determines the desired characteristic equation, which is S minus beta 1 times S minus beta 2 until S minus beta n equals 0. These are the desired eigenvalues. The observer pools must be 2 to 5 times faster than the controller pools to make sure the estimation error converges to 0 quickly. This will make the response quicker. This means that the observer estimation error decays 2 to 5 times faster than the state variable. Such a faster decay of observer error compared with desired dynamics makes the controller pools dominate the system pools. The controller pools will be the dominant pools in the system. It's important to note that if sensor noise is considerable, we may choose the observable pools to be slower than 2 times the controller pools, so that the bandwidth of the system will become lower and smooth the noise. We need the bandwidth to be smaller, and this will smooth the noise in this case. In this case, the system response will be strongly influenced by the observer pools. The observer pools will be the dominant pools. If observer pools are located to the right of the controller poles in the left half of the S-plane, the system response will be dominated by the observer poles rather than the controller poles. If the poles are to the right of the controller poles, then they will be the dominant poles in the system. In the design of a state observer, it is desirable to determine several observer gain matrices, KE, based on several different desired characteristic equation. For each of the several different KEs, simulation tests must be run to evaluate the resulting system performance, to obtain the system performance. Then we select the best KE from the viewpoint of overall system performance, the all matrices of the system performance, which is the settling time, rise time, and the maximum overshoot, and so forth of these parameters. In many practical cases, the selection of best KE boils down to the compromise between speedy response, the speed of the response, or a fast response, and sensitivity to disturbance and noises, to be more sensitive to disturbances and noises. We will see now example number 1. We have the system with given equations x1 dot x2 dot equals 0, 20.610 times x1 x2 plus 0, 1 times u, and y equals 0, 1 times x1 x2. We use observer-based approach to design state feedback control such that u equals negative k x hat. Design a full order state observer. Assume that the desired eigenvalues of the state observer are beta 1 equals negative 10 and beta 2 equals negative 10. First of all, we'll check system observability. We construct the observability matrix, which is C, CA, C equals 0, 1, and C times A equals 1, 0. We get the rank of the matrix, and we have the rank equals 2, which is a full rank matrix as the rank of the system. Then the given system is completely state observable, and the determination of desired observer gain matrix is possible. We can design the state observer as the system is completely state observable. First method is the direct substitution method. We have a Si minus A plus Ke determinant equals 0. Ke, we assume it equals Ke1 and Ke2. Then we obtain S times the identity matrix equals S0, 0, S minus LA 0, 20.610 plus Ke times Ke, which is Ke1, Ke2 times C, which is 0 and 1. Then we get this equation for the determinant S square plus Ke2S minus 20.6 plus Ke1. We will equate this equation with the equation obtained from the desired eigenvalues, which is negative 10, negative 10, S minus beta 1, S minus negative 10, S plus 10, times S minus beta 2, which is S plus 10. We get S squared plus 20, S plus 100, equals the equation in the previous slide, S squared plus Ke2, S minus 20.6 plus Ke1. We will equate the coefficients for S power 1. We get Ke2 equals 20, and we equate the coefficients of the S power 0. We get 100 equals negative 20.6 plus Ke1, then Ke1 equals 120.6, which is Ke1. Now we will write the equation for the full order state observer. X hat dot equals A x hat plus BU plus Ke times Y minus C x hat. We substitute by A times x hat 1 x hat 2, B 0, 1 times U, and Ke 120.620 times Y minus C 0, 1, and x 1 hat x2 hat. We will multiply the matrix, this matrix inside the bracket. We get 120.620 times Y minus 120.620 times 0, 1 times x1 hat x2 hat. Then we will have the final equation, which is like this. The second method is using the transformation matrix Q. First of all, the given system is already in the observable canonical form from the previous example. Hence, the transformation matrix Q is I, which is the identity matrix. We got the characteristic equation Si minus La, which is S squared minus 20.6 and equated to 0. We have A1, which is the coefficient of S squared of S equals 0, and coefficient of S power 0 equals negative 20.6. Then the characteristic equation, the desired from the eigenvalues, S minus beta 1 times S minus beta 2 equals S plus 10 times S plus 10. Then we have S squared plus 20S plus 100. The coefficient of S power 1 equal 20, and the coefficient of S power 0 equal 100. Then we construct the KE matrix, which is alpha 2 minus A2 and alpha 1 minus A1. Alpha 2, which is equal to 100, minus A1, 100 minus negative 20.6 equal 120.6, and for alpha 120 minus A1 0 equals 20. The last method is Ackerman's formula. We get KE equals phi of A times the C CA inverse times the 0, 1, which is the B matrix. We get phi of A equals A squared plus alpha 1 A plus alpha 2 times I. We have alpha 1 equal 20 and alpha 2 equal 100. This is from the equation of S minus beta 1 times S minus beta 2. Then we substitute A squared plus 20A plus 100I. Then we get phi of A squared, we get matrix A squared plus 20 times matrix A plus 100 times identity matrix, which is 1, 0, 1, 0, 0, 1. We get phi of A equals 120.6, 20 for 112 and 120.6. Then we get KE, which is phi of A times the CA inverse times 0, 1. We multiply the phi of A matrix times the CA matrix, which is 0, 1, 1, 0 inverse, times B, which is 0, 1. We get KE equals 120.6 and 20. We substitute for the system equation x1 dot hat dot x2 hat dot equals the A matrix times x1 hat x2 hat plus B times U plus KE. We have obtained 120.6 and 20 times Y minus C times x hat. We will take this vector and multiply it by the bracket 120.6 and 20 times y minus 120.6 20 times 0, 1, then times x1 hat x2 hat. Then we multiply these two and collect or add the values multiplied by x1 hat x2 hat by the first matrix to get the A matrix, complete A matrix, equals 0, negative 100, 1, negative 20, x1 hat, x2 hat, and 0, 1 times u plus 120.6 and 20 times y. Example 2, we have design the regulator system for the following plant x1 dot x2 dot 0, 20.6, 1, 0, x1, x2, 0, 1 times u, y equals 1, 0 times x1, x2. The desired closed loop pools lambda 1 equals negative 1.8 plus j 2.4 and lambda 2 equals negative 1.8 minus j 2.4. We need to compute the state feedback gain matrix K to place the pools of the system at the desired locations. Suppose we use the observer state feedback control instead of the actual state feedback. The desired eigenvalues of the observer are beta 1 negative 8 and beta 2 negative 8. Obtain the observer gain matrix KE and draw the block diagram of the observer feedback control system. This is left for exercise to the next lecture. See you in the next lecture.